Yesterday, we talked about Vesper. We talked how to go from the Lewis structure to the 3D, to the molecular geometry of the molecule. Today, what we're going to do is we're going to use this molecular geometry, this Vesper theory, to figure out whether the molecules are polar or non-polar. Now, this property, whether the molecule is polar or non-polar, affects a lot of properties of the molecule. The most important one of them is where they dissolve. Does it dissolve in polar stuff or non-polar stuff? There is a general rule which says like dissolves like. So a polar molecule will dissolve in a polar solvent, but not in a non-polar one. And this is why we're going to spend kind of this whole lecture talking about how we figure out whether the molecule is polar or non-polar. So as we all know that water, which is the universal solvent on the earth, is a polar solvent. So what we're going to do is we're going to figure out whether those molecules polar, that means they dissolve in water. If they are non-polar, that means they don't dissolve in water. And this is the case for oil and water. When we add oil to water, they form two phases, upper phase and lower phase. Sometimes if you add something which is non-polar to a solvent which is non-polar, they dissolve each other. And this is the case when you dissolve oil with any hydrocarbon, any other benzene, toluene, any of these, they will dissolve with each other. So this is why we're going to spend the whole lecture on polarity, because later on you need to know whether this molecule dissolves in water or not as you go through the other lecture, the other courses. So let's first start. What is polarity? What does that mean, polar and non-polar? This is just so. Do you remember when we were talking about ionic compound and covalent compound, and we said that in ionic compounds like NaCl, that there is a total loss of electron and a total gain of electron, and this is the definition of ionic bonding: is total transfer of electron from one to the other. So those are ionic compounds. Then we talked in chapter 2 or 3, we talked about covalent bonding, and we said that covalent bonding is not loss or gain, it is sharing of electrons. And we said that that's occurs mostly between all group 4 to 7A, the non-metals, when they make bonds together, they form covalent bonding. And an exception is hydrogen from group 1A. It also do a covalent bonding with group 7A and 6A and 5A and 4A when they do bonding. Now, when we talked about that, we just said sharing, but we didn't describe, is this sharing a 50-50 sharing? Is the electron exactly in between the two? Is it more toward one than the other? This is what we're going to talk about today. So let's say I have a F2. So this is the Lewis structure of F2. The electron in the case of F2 are exactly in between, 50% share of electron in the F2. Why? Because both of them have the same electronegativity. And we talked about electronegativity before. We said that electronegativity is the ability of an atom to attract the electron toward it. So the atom which is more electronegative in covalent bond, they prefer the electron. The electron will spend more time toward those atoms with high electronegativity than those of low electronegativity. In case of F2, it is a 50% share. That means the electron is exactly in between the two electrons, between the two atoms. In case of hydrogen iodide, which is the case in here, it's again a covalent bond. We don't talk about polarity if we don't have a covalent bond. So the first thing, we have to have a covalent bond to talk about polarity. So in case of H iodide, which is the case in here, we have covalent bond, yet the electrons spend more time towards the iodine rather than the hydrogen. And the reason behind that iodine is more electronegative than hydrogen. So because the electrons are spending some more time around the iodine more than the hydrogen, it's going to have something that we call partial charge, and we refer to it with this sign, something like that. And we call this partial negative charge. Partial negative charge. And that partial negative charge is just to say that the electron is not totally lost or gained as in the case of an ACL. The whole idea that the electrons are spending more time with the iodine than the orbital of the iodine than the hydrogen. So always in a covalent bond, the atom with higher electronegativity is going to have a partial negative charge, and that's which is with less electronegativity, it's going to have a plus partial charge. That means, as we understood before, that a plus means a loss of an electron, but here it's a partial, it's not even loss. It's only saying that the electron is more toward the more electronegative atom. Now, this causes a dipole moment. We call that a dipole moment. That means, and all what it means, all what this arrow means, that the electrons that are in share are more toward the iodine than the hydrogen. And we refer to it by an arrow, and we call this the dipole moment. So, which implies that this molecule is polar. Why? Because it isn't an equal share, and it have now a partial positive, and a partial negative charge in there. Now, the first time we figured out about this kind of thing, which is polarity, is when we put the molecule inside an electric field and we turn on the electric field. What happens that those molecules align themselves so that their partial positive charge, I have to use another color, will be more toward the negative side and the minus toward the plus. So this is how we figured out that this is okay for molecules, by using the electric field and looking at the molecule and see them aligning themselves along when an electric field is applied. So this is how we figure out. So first of all, it should be a covalent bond to talk about polarity. The second thing, there should be a difference in electronegativity between the two atoms to talk about polarity. If for example, in the case of F2, the delta chi, which is the difference in electronegativity, equal to 0. Why? Because both of the atoms are the same atom, so definitely it's going to have the same electronegativity. So in this case, it is non-polar. And the reason behind it, that the difference in electronegativity is 0. So just a reminder, I'm going to remind you about the trend of the electronegativity in the periodic table. So again, it is the ability of that atom to attract electrons towards it. This is the definition of electronegativity. And it increases this way, the same as ionization energy in the periodic table. The only exception is hydrogen. As you can see in this periodic table, it is placed in the middle because it have a higher electronegativity than group 1A and 2A. Okay, so let's take some examples. So the first example is H2. So first of all, we know that H2 gonna have a covalent bond because it is the only exception from group 1. So it is a covalent bond. The second thing I'm gonna think, okay, is there a difference in the electronegativity? Clearly that the delta chi, which is chi H minus KH, it's gonna be equal to 0 because it's the same atom. So it's gonna be non-polar. Okay? In other words, all the homo diatomic compounds are nonpolar. What do I mean by that? F2, H2, Br2, Cl2. All of these are nonpolar. The reason behind it, the difference in electronegativity is 0. So no one will be willing to take the electrons more time than the other. They have exactly the same ability to attract the electrons. So it's a 50-50 share. That applies as we go. I2 S2O2 N2, any homo diatomic atom is going to be nonpolar. Okay? And the reason behind it is the difference in electronegativity is very tiny small. Now let's go to the example of HF. Again, HF is a covalent bonding. Now, I know that the hydrogen have 2.2 as electronegativity, and we know that fluorine is the atom with the highest electronegativity. So I know for sure that the electron, due to the difference in electronegativity, which is about 1.8, that the electrons will spend more time toward the fluorine than the hydrogen. So that implies the hydrogen gonna have partial positive charge, and the fluorine gonna have a partial negative charge, which implies that this compound or this molecule is polar. Now, for the case of lithium fluoride, first of all, it is ionic compound, because it's a group 1 with a group 7, and we know that it is ionic compound. The reason behind its ionic is that the difference, if we do the difference in the electronegativity, is very high. It's about 3. So the fluorine decides to take the electron. This is why it is an ionic compound, because the fluorine is very high in electronegativity compared to the lithium, so that it decides to take the electron. So the lithium gives up the electron for the good reason that it's going to look like a noble gas, the fluorine going to look like a noble gas, and it is a win-win situation. So we don't talk about polarity when we talk about ionic compound. Most ionic compounds are soluble in polar compounds because they have a total plus and a total minus. We talked about some compounds in chapter 3 that they are partially soluble or insoluble in water. That the table, if you remember, the table of precipitation or solubility, but most of them they will dissolve, some others will not. So always when we talk about polarity, we talk about covalent bonds, not ionic compounds. Now, this is the rule for compounds like HF. But what if I have something like methane? How am I going to figure out the polarity? This is a very complex molecule in the sense that it have a geometry of tetrahedral, right? So it's not like as I see it on the paper that it's more like tetrahedral molecule, and I know that the hydrogen is less electronegative than the carbon, so I'm gonna have 1, 2, 3, 4 dipole moment pointing toward the carbon because the carbon is the most electronegative. And it's gonna be, and the way that we usually figure it out as chemists, we begin adding those vectors together using the geometry and trigonometry. And since we are not in a chemistry class, I'm going to give you kind of the bottom line of that. Otherwise, you have to deal with the vectors every time I give you a molecule. So what I'm going to do, I'm just going to give you the bottom line, but you have to carefully listen to what I'm going to say in the next slide, okay? And this is all based on the idea whether those vectors going to cancel each other or not in the case of polarity. So, the molecule is nonpolar if it is symmetrical, and I'm going to put 3, 4 lines under symmetrical. Symmetrical. So the first condition that it must be symmetrical, and if it has the Vesper model AX2, AX3, AX4, AX5, AX6. In short, all those AXs that they don't have an E and they are symmetrical, they're going to end up nonpolar. Okay, I'm going to repeat this whole situation, because if you misunderstand it, you're gonna get the polarity wrong. So the first condition is symmetrical, that the molecule as a whole is symmetrical. The second condition, if it has a Vesper model AX2 or AX3 or AX6 or AX5, any of the AXs without any of the AX without an E, and all the X's are the same, or it is symmetrical, it's going to end up being a non-polar molecule. Okay? This is the first condition. Now, the molecule is going to be polar if it is non-symmetrical, and if it has an E in its Vesper model. In other words, if it has a lone pair on the central atom. Example of that, AX2E, AX3E, AX4ED. Now, for both conditions, there are exceptions, and we're going to talk about those, and this is why I prepared this table for you guys, so that, and I'm going to walk you through it so that you understand what all of these. You don't have to know everything on that. You have to know this rule. Those only in this slide, you need to know those two rules, and I'm going to walk you through those just because I'm giving you more examples, and it will illustrate the things that I talked about symmetry and about heat on this slide. So let's go to this one. If you don't have this this handout, please feel free to come down and get it right now, in case you don't. Okay. What about you stay? Jake will, I thought you were one or two. Please, Jake, may you please? And Jake will hand out that. Okay. So the table starts with something called Vesper type, and then it states non-polar, polar. So in other words, okay, raise your hand if you don't have it so that Jake can hand it in. Okay. So we're gonna start with AX2 in there. Okay? So it says that if you have AX2, if the Vesper model is AX2 and it is symmetrical, we're gonna start with CO2. We know that CO2, this is the Lewis structure of CO2, and we know for sure that it is AX2. First of all, it is symmetrical. CO2 is symmetrical because if I put a plane in here or a mirror, it's gonna look exactly the same. So this is why CO2 is non-polar. Why? Because it's symmetrical and it has AX2 as a Vesper model. Okay? Now let's look at the exception of that rule. The exception of that rule, if I have N2O. And N2O, this is the Lewis structure of N2O. If I put a mirror, it's not symmetrical. Why? Because I have the terminal atoms are not the same. One is N, the other is O. That's make it a polar. Why? Because it's not symmetrical. Get the idea, guys? If you did not raise your hand so that I repeat, because if you don't understand how to read this table or to understand what I'm talking about, it's gonna be hard to follow up with me. So all of us are on the same boat? Okay, very good. Now I'm gonna go to the AX3, which is also an AX3 that doesn't have any E. For BF3, so I have F. It is symmetrical. First of all, it is AX3 and it is symmetrical because all the F's, all the terminal atoms are the same. This makes it a non-polar molecule. The same as the rule states, if it is symmetrical and it has AX3 or AX5 or AX6, it's gonna be non-polar. The exception for that is COCl2. In COCl2, this is the Lewis structure. And in this case, definitely it's not symmetrical anymore because the X's, the terminal atoms are not the same, and that's make it a polar molecule, although it is an AX3. Now I'm gonna go to AX4 again. For the case of methane, which we just talked about a minute ago, we have, this is the Lewis structure. And since it is AX4 and all the terminal atoms are the same, HHH, it is non-polar. An exception for that is CHClHH, which is this one in here, CH3Cl. And the reason behind it that now it lost symmetry because the terminal atoms are not the same. There is at least one of them that is not the same. And this is gonna make the molecule polar, although it is AX4. Okay, AX5 for PCl5, this is the Lewis structure. And as we know, it is bipyramidal. It's trigonal bipyramidal. So it is symmetrical because all the Cl's and all the terminal atoms are the same, so it is non-polar. An exception of that is PCl4F. That means when one of those terminal atoms are not the same, and that's make it a polar molecule because it lost symmetry. The terminal atoms are not the same. The same for AX6. CF6 is non-polar because it is AX6 and it is symmetrical. All the terminal atoms are the same. As you can see, probably if you put CF5Cl, it's going to be polar because the symmetry is broken. Can everybody see the trend that we're going through? Very good. Now we're going to move to the E. Everything that has an E in its Vesper model gonna be polar, and there are some exceptions, and I'm going to show you those exceptions. I'm going to use the green color just to differentiate between. So AX2E2, an example of that is SO2, which have a lone pair in there, and it's going to be polar. AX2E2, and this is water, and definitely it is polar because it has an E in its Vesper model. And the reason behind the polarity because the lone pairs that are there, they are making this molecule unsymmetrical, and it doesn't, and the dipole moment does not cancel in there. Now AX2E3, XEF2 is, for the AX2E3 we have BRIF minus. It's gonna look non-polar. It is gonna be polar because it has an E. The exception of that, this is the exception, is XEF2. For XEF2, I'm gonna insert in here. For XEF2, this is the Lewis structure, and we have 1, 2, 3 lone pairs here, and it happens that it's gonna cancel the two dipole moment gonna cancel each other. So it is symmetrical. If you look to this molecule, it is symmetrical. Although it have AX2E3, it's still symmetrical, and this is why it is the exception and it is non-polar. This is one of the compounds that has an E in there, that has a lone pair in there, and it is non-polar. Mostly all the molecules that has lone pair, that means in their Vesper model they have an E, they're gonna be polar. An exception of that is XEF2. The others, all the ones that has an E, like NH3, it's gonna be polar. CLF3, which is AX3E2, it's gonna be polar. There is no example where it wouldn't be. It would be a non-polar. AX4E, it's also a polar molecule. The other exception for the E is XEF4, the xenon exception. It has E, but because it's symmetrical, the same reason as XEF2, because it's symmetrical, the symmetry causes that the dipole moment to cancel each other, and it is non-polar. Okay? So in short, all the E's are polar. The two exceptions are XEF2 and XEF4, or any example in which it has an E yet it is symmetrical. All the ones that have AX3, AX2, AX5, AX6, if they are symmetrical, if all the terminal atoms are the same, they're gonna look non-polar. Okay? You don't need to know everything on this table. All what you need to know that there are some exceptions for AX, for the E's, for the X's, and keep that in mind. Okay? And now what we're gonna do is some eye clicker just to get used to the idea. So your first step is draw the Lewis structure, go to the Vesper model, figure out what's the Vesper model, remember the rule, the slide with the rule, and from there you'll determine whether it is polar or not. And we're gonna start. I know that some of the examples that we're gonna do is listed on the table. Please don't just pick it from the table. Do the Lewis structure, because in the exam you're not gonna be given this table. So draw the Lewis structure, figure out the Vesper model, and determine whether it is polar or not polar. I'm gonna stop it at 120. Okay. So I'm going to stop it at 120 and check what you think, guys. And I have C as 87%. C is the right answer. So first of all, you have to go through the Lewis structure, draw the Lewis structure, figure out the number of electrons. Then after that, the Vesper model. C is the central atom, the two oxygens are the terminal, no E on the central atom, no lone pair, so it is AX2 that implies it's linear. Since it is linear and the terminal atoms are the same, so therefore it is non-polar. Okay. What about the X3? Okay. So I'm gonna stop it at 120 and check what you think, guys. And I have 65% for BB is the right answer. So it is, this is the Lewis structure of F3. Then I'm going to take it from the Lewis structure to the Vesper model, which is AX3, which is a trigonal planet. And since it is AX3 as a Vesper model and all the terminal atoms are the same, so it's going to be non-polar. We'll do some more. What about an H3? check what you think. And I have C as 62%. C is the right answer. So this is the Lewis structure of ammonia, which is an H3. That implies I'm going to take it to the Vesper model to study. So it is AX3E, which is pyramidal. Wait a minute. Pyramidal. And since it has an E in its Vesper model and it's not symmetrical, so it's not XEF2 or any of those, so it's going to be polar. Okay, let's do some more. So we have CH4 and CCl4. Both are polar, both are non-polar. CH4 is polar, CL4 is non-polar. Choose, what do you think? I'm going to stop this at 2 because you have to contrast to make it all.
So wait, this one? Polarity these two. This one's not bad. This one is. These two are.
This two looks much better. It doesn't go.
It's gonna be. It's actually when we built this.
So let's stop it at 2 and check what you think.
Okay.
Oh, it's PR. This one's gonna be bent.
And I have B
And this one's
at
gonna be
72%. B is the right
tetrahedral.
answer.
But what's gonna happen?
So the
like,
reason
this
I
is the
put
central
this
atom.
question in
It's gonna be shaped
there
like this.
the following.
These two are
First
fluorines,
of all, I
these two are
have
hydrogens,
methane. This is the
and this
Lewis
side's gonna be
structure of
nitrogen,
methane,
essentially.
which is CH4. And this is the Lewis structure of CH4. Now, both of them gonna be AX4 tetrahedral, AX4 tetrahedral. The only difference, both of them, they are AX4, they are tetrahedral, they are symmetrical. The only difference is that this carbon, in this case, the dipole moment will go from the carbon to the Cl. In this case, it's gonna go from the hydrogen to the carbon. Yet both of them gonna end up being non-polar. Why? Because again, that's gonna cancel. In this case, the Cl is more electronegative than the carbon. In this case, the carbon is more electronegative than the hydrogen. So it doesn't matter as long as both of them are symmetrical and AX4, and they are symmetrical and they have an AX4 as a Vesper model, tetrahedral structure. Okay, let's do some a little bit more challenging. And it's going to be numerical, so you're going to answer 1, 2, 3, either 1 or 2 or 3. Which of the following molecules below are polar? I'm going to stop it at 215 so that you get the chance. You already have the Lewis structure. Each one of them is written in its right Lewis structure. stop it right here and check what you think. And I have 2 as 57%. 2 is the right answer. Yet the percentage is not that very high. So let's start with A, DF3. It is AX3. All the terminals are the same, so it's going to end up non-polar. It's AX2. E2, it's a bent. It has an E in there, so definitely it is polar. This is AX4. The terminal atoms are not the same, so the symmetry is broken. It may look to you that in this case, as it is, that it looks symmetrical, but in the tetrahedral it wouldn't. Remember that is not on the plane. It's gonna have the F and the H different, so it's gonna end up being polar because there is no non-symmetry, no symmetry. So that's make B and C are polar, which make 2 the right answer. Okay? Let's go a little bit to challenging one, another challenging one. And now you're gonna go back to A, B, C, D choices. So which of the molecules below are non-polar? And here I didn't give you the Lewis structure, so you have to draw the Lewis structure yourself. Okay. I'm going to stop it right here and check what you think. And I have A to be 69%. A is the right answer. So I'm going to start with PF5. So this is the Lewis structure of PF5 with definitely all the lone pairs on the fluorine. So I'm going to try to do it fast. So it is AX5. It is symmetrical, so it is non-polar. CH2Cl4. This is the Lewis structure with definitely the lone pairs on the Cl. So it is AX4, yet no symmetry. Therefore, it is polar. SO2. So it is AX2E2. It is a bent and it is polar because it has an E in there. Okay? That makes that the only non-polar compound is PF5. That makes A is the right answer. Okay, let's do this one. And this is numerical. I'm going to go back to the numerical. Which of the molecules below is polar? I'm going to stop it at 2 minutes. Great. I'm gonna give you some more time because I can see that some people get there. I'm gonna stop it at 2:30. By the way, you can change your answer at any moment you want, and I'm gonna get the last answer you put in there. Okay. So I'm gonna stop it right here and check what do you think. And I have 36% for 5, but this is a very low percentage. We've gone to 70, now we're back to 36. So let's see. First of all, XEF2, this is the basic structure of XEF2. So it is AX2E3, but it is the exception of all the E because it's symmetrical. So it is non-polar. CO2, we did it in more than one question, so by now I think everyone knows that it is AX2 non-polar. F2 is definitely non-polar for one good reason. It is one of the diatomic homonuclear like F2CL2BR2I2N2F, all of these O2, they are non-polar. They are non-polar because the delta difference in electronegativity is 0, equal to 0. SO3, so we have SO3, this is SO3, it is AX3, definitely with the lone pairs in there, and it is non-polar. And the last one, SF4, which is going to be SF4 with definitely the lone pair. I'm going to try to do it fast with all the lone pairs there. And one lone pair on that, so AX4E, it has a knee, so it is polar. So the only one that is polar between all of these is, okay? Now, let's see, I think I should pick up one. Okay. What about this one? Which one of these is polar? Which one is polar? A or B? I'm gonna open the iClicker.
What's the next one?
Be right.
Oh, this is a question?
Yeah. Your turn.
Which one is what? Is it porn? Or which one is porn?
I'm gonna sort it at once.
Yeah.
Okay, and I'm gonna talk about it on Wednesday because I need at least 4 minutes to explain what's going on with this. Okay? So put your answer and you can leave if you want.
You can leave if you want. Because everyone
Oh,